Hello, my name is Tom Kelly from the University of Manchester, and today I'm going to talk to you about a Python-based crop growth model called AquaCrop-OSPy, which I developed with my supervisor, Tim Foster, as part of my PhD in intelligent irrigation management using crop models, optimization, and machine learning. So to give you more background and context around my PhD, agriculture currently uses more fresh water globally than any other sector, and irrigation makes up the majority of that. And with climate change and increasing population, the demand for freshwater resources is only going to increase from all sectors. And so there's kind of increasing interest around improving irrigation water efficiency. And one of the main tools helping us to do that is crop growth models. So these are really powerful tools which simulate crop growth in response to climate and management practices. And often experiments are too costly and time-consuming to do in an actual field, and so if you can calibrate a crop model to a specific field and crop environment, then you can conduct experiments a lot faster and a lot cheaper than you could in an actual field. So these type of models come in all different shapes and sizes. Some are designed more for usability, and they often come with a GUI interface for users to interact with, and a few others are code-based, which kind of allows for a bit more flexibility and advanced use cases. So applications of these models can be all the way on a large global scale, looking at kind of climate change, impact assessments, or on a much smaller local field scale level, where we can, for example, evaluate different irrigation management strategies. So it's really on this second one that a lot of my focus has been on, and so I developed AquaCrop-OSPy. So this is a Python implementation of a crop water model called AquaCrop, which was developed by the UN FAO, and this model aims to simulate crop response to water stress in particular. And so AquaCrop-OSPy, it builds on two other open source versions of AquaCrop, the main one being in MATLAB, which was developed by my supervisor Tim, and it was mainly in that source code, which helped me convert over to the Python version. And there's also recently been an R version as well. We've just got a peer-reviewed article published in Agricultural Water Management on the model, and so the links to that are on the GitHub or the forums. And so why would we want to make this Python version? Why not just use the MATLAB and R versions that are already around? So firstly, I'm sure I don't need to stress some of the advantages of a Python version at SciPy, but Python is just a really great language to work with, and I've designed this model in mind so that only basic Python experience is required in order to use the model. So it makes it a lot easier for non-coding or Python experts who may have interest in this kind of research to try and run simulations really quickly. It's fully self-contained and you just pip install it. So it's really easily integrated with other Python modules, such as optimization algorithms. We've got a series of Jupyter notebooks which guide the user all the way from building your first model, running your first simulation, all the way to optimizing irrigation strategies and doing climate change impact assessments. We've also heavily kept resources like Google Colab in mind during the development, and so all the Jupyter notebooks link to Google Colab, and this enables anybody with an internet connection and a Google account to install and run the model and conduct really sophisticated analysis without the need to locally install and can use the free computational resources in the cloud. So for the rest of this talk, I want to quickly guide you through running your first crop simulation, and then I'm going to talk through a couple of more advanced use cases which I've been working on as part of my PhD, such as optimization of irrigation scheduling, and then also try to schedule irrigation using deep reinforcement learning. And then finally, I'll touch on one of the newer applications we're working on, which is a web application using the Streamlit package. So running your first simulation. So you'd want to go to the source code on GitHub, and in the README you'll find a bit of model description and some links, and you will also at the bottom find a bunch of Jupyter notebook tutorials. The whole library, by the way, was built using the mbdev package, which is a framework made by the guys at Fast AI, which I thought was a really great and useful package, and you can build this whole library using just Jupyter notebooks. So that was really useful. And we also have a forum where users can discuss bugs and future development of the model and research applications. So if you scrolled all the way down and found the first tutorial and clicked on that one, it would take you straight to Google Colab, and we'll have some description of the model, and if you scroll further down you'll be able to pip install the model and then import any of the functions that you need. Once you've done that, you will be able to build all the components you need to then run your simulation. So the first thing AquaCrop wants is your climate data, so it needs daily measurements of minimum and maximum temperature, precipitation, and your evapotranspiration. So not to worry if you don't have that kind of data to hand. We have a bunch of built-in example climate data files that you can easily use. So once you've specified your climate data, next you want to specify your soil type. Again, we've got a bunch of built-in soil types for people to use, as well as a few built-in crop types. And so once you've specified your climate, soil, and crop, last thing is your initial water content at the start of the simulation. And you can also specify your management practices, such as your field management and your irrigation management, but these don't need to be specified in this case. It's just a rain-fed crop field. So we can package all these components up into an AquaCrop model object and specify our simulation start and end date. We then want to initialize the model and then run all the way to the end of the simulation. Once the model is finished, we can then look at all of our output files. This one is just a summary detailing for each season in your simulation what was your yield and your seasonal irrigation. So that was running a really quick simulation, and if any of that went too fast, you can check out the notebook, which is a lot more text and description guiding you through it. So looking at the next example case, optimizing irrigation scheduling. So if we take the example of Nebraska, which has the largest number of irrigated acres in the United States, the figure here shows us the types of information that Nebraska farmers use in order to help them schedule irrigation. So this data is from the USDA Farm and Ranch Survey. So ignoring the crop condition and feel the soil, the only type of information that's been increasing year on year has been the use of soil moisture sensors, which are now at number 3, and so this now makes up about a third of Nebraska farmers are now using these soil moisture sensors. And when you have these in your field, what will often happen is that you'll measure your soil water content with the sensor, and you'll specify a threshold so that if your soil water content in this figure, it'll be the blue line, if that water content dropped below that threshold, you would schedule irrigation, you trigger irrigation. And so what we might want to do is, can we use a model like AquaCrop to optimize these thresholds in order to maximize profits or yield for a given water allocation? And so the code in order to do this kind of optimization is actually quite simple with AquaCrop, where we can define a function called run model, and it's got all the same stuff we saw in our introductory model, where we define a crop, a soil type, a initial water content. Now we are also defining our irrigation management, and then we package it all into a model, run, and return our output files. We can also create an extra function, which will be our cost function that we want to minimize, and this function just runs the model and returns your negative yield. So that's what we want to minimize if we want to maximize yield. And as an example, we can throw this in SciPy's fmin to try and find the optimal set of thresholds that maximize yield for a given water allocation. And when we run an example like this, we can produce something that's called a crop water production function. So these plots are really, really useful, and we can a producer can generate this plot using the code we've outlined in the last slide for their chosen crop and soil type and climate, and they can see that if they have 200 millimeters per hectare of water allocation for the next season, this is the irrigation strategy set of thresholds that they will want to use for the next season in order to maximize profits. So going slightly beyond optimizing sets of thresholds, we can move on and see if we can try an even more complex type of irrigation strategy and see if we can do even better. And for that, we might want to try deep reinforcement learning. So for any who are not familiar, and forgive me for brushing over the details for the sake of time, deep reinforcement learning is a type of learning algorithm that has had so many notable successes in the last decade, where this algorithm has been able to learn how to navigate really complex game environments, such as chess and Go and StarCraft, and also has had some recent successes in the field of robotics. So there's quite a lot of optimism around this technique, and in the last couple of years there's been some papers that have been quite optimistic about using deep reinforcement learning for irrigation scheduling. So in order to try out this technique and try and perform quite a robust, or at least a fair comparison, to just optimize thresholds, we used the case study of maize production in Nebraska, and instead of just using historical years, we feed these historical years into a weather generator. And so this weather generator can then generate 100 synthetic climate years, and we separate these into 70 train and 30 test years. And so they all come from the same distribution, and so it essentially just takes out the climate change and changes in CO2 levels and any kind of long-term trends in weather, so that we can just focus on dealing with climate variability that happens year to year. We give our agent a set of observations every 7 days, and it can make irrigation decisions. And at the end, it will receive the profit as a reward, and we then use the PPO algorithm to update the agent's decision making in order to try and maximize those profits. So firstly, looking at the left plot, we can see our learning curve for our PPO algorithm. And firstly, we can look at our training profits, and we can see that compared to our optimized soil moisture threshold, our algorithm does surpass the optimized soil moisture thresholds. And just before I forget, just going back, the reason why we've done this kind of synthetic training climate years as well is because the average profits that we kind of want to maximize are the same for the training and the testing sets. That's why we've done it that way. So so for the training years, the agent does very well. However, for the unseen test years, the algorithm never quite reaches the heights of the average profit achieved by the optimized soil moisture threshold. And so I ran a second analysis, this time by removing the rainfall, and you can see without all this essentially free irrigation water coming from the rainfall, the average profits decrease quite dramatically. However, when you remove all this this rainfall variability from year to year, all of the training and test years, they all become a lot more similar to each other. So what it does is it allows the PPO algorithm to overfit essentially to this environment, instead of having to try and generalize towards all these different types of potential rainfall patterns. And so what we can kind of, or the conclusions we can kind of draw from these initial results is firstly that the DRL agent is able to overfit to a specific year, that we've done other tests on the side on specific years, and it can also overfit to a set of training years. However, when evaluated on an unseen test year, which will be what it has to deal with if it's actually applied in a real field situation, it's unable to do better than simple optimized sets of soil moisture thresholds. So what this might imply is that DRL is better suited to a more controlled environment, so maybe something like vertical farming, where there's less unknowns and less uncertainty. And just wanted to touch on that. It may not just be the case, or a simple answer as I should have trained it for longer and for using deeper networks and better algorithms, because each one of these agents would have to be retrained for each individual soil and crop and climate system. So if a company were to develop this kind of system and sell it to farmers, they would have to then spend the thousands of dollars retraining this agent for this new environment each time a new customer came through. So it may not just be the case that training it for longer and throwing more computational power is always the answer. And so finally, a very quick look at one of the newest things we're looking at developing with this model is a web application. So kind of almost going back full circle to the GUI-based crop models we talked about earlier. And with this web app, using the really great Streamlit library, we can let the user choose a location and a crop and a soil type and irrigation strategy, and what the model can then run a set of simulations and can give the user an estimate for how much irrigation water they might be expected to use in that region. And we can also give them over a range of different water allocations what types of yields they might expect to get. So these will always be kind of rough estimates, but it does make getting these rough estimates infinitely easier than it was before. So the future of this model, so we've got our forum and a really growing community of users where we're discussing bugs and future development. There's a lot of extra features that we're currently working on and adding in extra crops and more tutorials, and we have the web app. So we're really excited about it. And yeah, thank you all for listening, and I'll be happy to answer any questions.